Thank you to Squarespace for supporting PBS.
Half of the universe is filled with expansionist alien civilizations, and it's only a matter of time before they reach us. Okay, that sounded a little sensationalist, but it's also the claim of a recent astrophysics paper. Let's see how they came to that conclusion and whether we should take it seriously. We humans have been around for only a blink of an eye compared to the 13 billion years since the Big Bang. But even the current age of the universe is itself a blink of an eye compared to the amount of time yet to come. Stars will continue burning for another 100 trillion years, and the heat death of the universe is a googol years in the future. That's one with 100 zeros. From this point of view, we are living pretty much at the beginning of the universe. At the same time, when we look at the sky, we see stars, galaxies, but not a galactic empire in view. We see no evidence of life out there, which may mean that humanity is super early in the history of life in the universe, which I guess is pretty cool if you think being first to a party is cool. But it's also weird. See, we have this thing called the Copernican principle, which states that we shouldn't expect to find ourselves in a particularly special place in the universe, named for Nicholas Copernicus, who showed that the Earth is not the centre of the universe as had previously been thought. We are in fact on a typical planet orbiting a typical star in a typical galaxy. But in principle, you can extend this principle to time. If life can appear for trillions of years, then it's suspicious that we find ourselves in the first billions. Of course, the Copernican principle has to compete with the anthropic principle, which states that we can only find ourselves at a location in the universe capable of forming and supporting observers. That's why it's not surprising that we are on a planet at all, rather than floating in a more typical environment, the freezing void between the galaxies. So perhaps there's also an anthropic reason for us to find ourselves at the beginning of time. Maybe the future history of the universe isn't as hospitable to life after all. This may sound like a lot of speculation. I mean, how can we know what the future history of the universe will be? Well, believe it or not, it is possible to say something about the earliness of humanity and the future of life just based on our arrival date and the apparent emptiness of the sky. And today, we're going to talk about a study that tries to do exactly that. To hear more about the anthropic and Copernican principles and how we can use them to calculate other surprising things about the universe, including our expiry date, check out our video on the doomsday argument. But today we're looking at the new paper by Robin Hanson, Daniel Martin, Calvin McCarter, and Jonathan Paulson. First, these researchers ask the question, how early is humanity? They try to answer it by building a simple model of the emergence and spread of intelligent life in our universe. And then they use that answer to propose something pretty wild. A proposal that gives the model its name, the Grabby Aliens model. But you'll have to wait to hear what that proposal actually is. First up, how do you determine humanity's earliness? Well, you start with a function called the appearance rate, which tells us how many intelligent civilizations are evolving from primordial goop at a given cosmic time. Using the appearance rate along with our current date, we can work out our civilization's birth rank. Of all the civilizations that will ever exist, what proportion came before us? If most have already appeared, then we are late and we have a high birth rank. While if most are still to come, then we're early with a low birth rank. To figure out this appearance rate function, the researchers start with what we know about when habitable worlds formed in the past or when they will form in the future. It turns out that most habitable stars are formed in a pretty short period of cosmic history. In the first couple of billion years, the universe didn't contain enough heavy elements for rocky planets to form. And around 20 billion years in the future, there won't be enough interstellar material left to form new stars. Habitable star formation will peak at around 15 billion years, so not so far away from our current date. There are a bunch of other factors that cause the peak, which we go into our episode on galactic habitable zones. Once a habitable star along with its habitable planets have formed, life needs time to evolve. And it needs a lot of time. We humans only appeared 4 and a bit billion years after our planet formed. But how long does it take on average throughout the cosmos? To answer this, the researchers use the hard steps model. To get from primordial goop to intelligent life, you need a sequence of fluke events. On Earth, that involved the first formation of self-replicating cells, the evolution of complex eukaryote cells, then multicellular organisms, then photosynthesis, sexual reproduction, developing giant brains, and various civilization and technological steps. All of these events are possible hard steps, extremely unlikely per year, but will eventually happen after waiting a very long time. The number of hard steps is a big deciding factor in how fast the universe can spawn intelligent life. If there are few hard steps, then civilizations emerge soon after their stars are formed. If there are many hard steps, it takes much longer. If we assume that humanity was not particularly lucky, in the sense that we didn't blast through many more hard steps than chance would normally predict, then it's possible to crudely estimate the number of hard steps that it typically takes to produce intelligent life, like us. The author's best guess is between 4 and 8, admittedly with some major assumptions. It should also be noted that the hard steps model is simplistic. For example, some steps may be easy, but may take a long time anyway, like due to the slow but steady build-up of biological complexity. Still, the hard steps model lets us write down a mathematical function for the appearance rate of life that depends on a single parameter, the number of hard steps. It also lets us say something about humanity's earliness based on the typical number of hard steps. The more steps there are in the typical evolutionary pathway, the earlier humanity must be. Another important question is, what's the time limit for completing these steps? How long do these habitable planets remain habitable? It's estimated that the Earth will only be habitable for another 1 billion years or so, after which the Sun will be too hot for liquid water to exist on the surface of the planet. So Earth will have 5 billion habitable years in total. If all habitable planets only last this long, then new civilizations would mostly stop appearing 5 billion years after the peak of habitable star formation, which, if you remember, is 20 billion years away. In this case, it seems like we're a little bit early. However, there's one big consideration that totally changes this picture. There might be other habitable planets that last a lot longer than the Earth. M-type stars, also known as red dwarfs, can live for thousands of times longer than our Sun, meaning they could have planets that remain habitable for trillions of years. If it's possible for life to evolve on these planets, then new civilizations could continue to emerge for trillions of years in the future. In this case, we are very early. The experts are split on whether red dwarfs are habitable. Since they're very dim, orbiting planets need to be very close to the star in order to have liquid water, which may be necessary for life. But planets closer to their star are more likely to be tidally locked. This can cause erratic climates and make any potential inhabitants vulnerable to solar flares. The authors of this paper argue that life could well evolve on red dwarf planets. After all, why should all life have the same requirements as Earth life? But this isn't the scientific consensus, and notably these researchers are not planetary scientists nor astrobiologists. So, there are two main deciding factors of our birth rank: the number of hard steps and the maximum lifetime of habitable planets. By throwing many combinations of these two parameters into their model, the researchers generated this diagram. Let's talk through it. Each point on this surface represents a choice of a hard step number and a maximum planet lifetime. And the colour of that point tells you your birth rank. Cold colours means we are typical, and hot colours means we're early. If only short-lived planets like the Earth are habitable, and there are few hard steps, then we were born at a pretty typical period of the cosmos. About 25% of civilizations were born before us. On the other hand, if red dwarfs are habitable, but it's easy for life to evolve, then we are in something like the first 0.1% of civilizations. Finally, if there are both long-lived habitable planets around red dwarfs, and there are many hard steps, then virtually all civilizations will result from very drawn-out evolutionary processes trillions of years in the future. There will be a billion times more civilizations born after us than before us. Okay, now we get to the wild proposal of this paper. The researchers ask the question, if red dwarfs are habitable and there are many hard steps, is there any other way to explain our apparent earliness besides extreme chance? The idea is to come up with some plausible scenario that limits the number of possible future civilizations, even in the case that we should expect them based on the emergence of habitable worlds and the hard steps model. The so-called grabby aliens model hypothesizes the existence of a cosmic deadline for the birth of new civilizations, some catastrophic event that will happen one day in the future that prevents any new intelligent life from emerging. But what could cause such a deadline? Well, we could. And by we, I mean all civilizations that emerge up to that deadline. The model claims that at some point in the future, all habitable planets will be occupied by rapidly expanding alien civilizations. No new life has a chance to evolve because every planet is already occupied by spacefaring advanced life. To reach this conclusion, the model assumes that every intelligent civilization has some chance of becoming a grabby civilization, a civilization that expands in every direction through space at close to the speed of light, making visible changes wherever they go, and that they stick around for a long time. Well, when we look at life on Earth, it seems that life has a common tendency to aggressively expand into new territories and niches. When thinking about our own society today, some might be skeptical that we're going to be able to expand through the cosmos at close to the speed of light anytime soon. But even if it takes us 1,000,000 years to work out how to expand into space and another 1,000,000 to cross the galaxy at 10% light speed, this delay will have basically no effect on cosmological timescales. The authors needed to tune the parameters of their model to cut out just the right number of future births of new civilizations to give us a typical run-of-the-mill birth rank. If grabby civilizations aren't common enough, they won't prevent enough future births to make us typical rather than early. But if they're too common, then we couldn't have evolved in the first place as Earth would already have been colonized. That actually allows us to estimate the number of civilizations needed to make sure that humanity isn't too special by being too early. But for that, we also need to estimate the speed of grabby expansion. We do that with a single surprisingly useful bit of information: the fact that we haven't yet seen any evidence of aliens through our telescopes. Counterintuitively, this fact implies that grabby expansion is incredibly fast, around 1/3 of the speed of light. How does this follow? Well, basically, if we could see grabby aliens in our skies, then aliens must be moving slowly since they are in our neighbourhood but haven't reached us yet. Instead, if we assume that they move very fast, then we wouldn't see them until they basically arrive on Earth. The emptiness of our skies and the constraint of making us typical observers is enough to determine all of the parameters of the model. The researchers then use the model to run a simulation of the emergence of intelligent civilizations over time, in which some civilizations become grabby and spread through the universe, ending with a universe totally full of life. The simulation tells us all sorts of weird and surprising things about how space is populated, at least given the assumptions of the model. It tells us that the colonization of the universe has already begun. In fact, around half of the volume of the universe is currently colonized. It predicts that only 1 in 1,000 intelligent civilizations eventually become spacefaring and spread through the cosmos. This could be because most civilizations destroy themselves before they get the chance, or choose not to take to the skies. And finally, it tells us roughly when we should expect to meet those grabby aliens. It gives us a best guess waiting time of around 500 million years. Don't expect to meet aliens anytime soon, even if they do fill half of the universe. I guess they're just not in the Milky Way yet. I'm not going to say whether the conclusions of this paper are right. Remember, this is a model, and its conclusions are only as good as the assumptions behind the model. But this paper is a nice example of how you can figure out a lot given very little. In this case, given literally nothing, at least in terms of our observation of the existence of other civilizations. But if these authors are right, and that's a big, big if, then it may be that our empty sky is one piece of evidence for a universe filled with aliens rushing in to grab this rare remaining patch of spacetime.
Thank you to Squarespace for supporting PBS. Squarespace is a website building and hosting company.
With Squarespace, you can connect with your audience and generate revenue through gated members-only content. Users can manage members, send email communications, and leverage audience insights all in one platform. But one of their most popular features is their collection of website templates that will help you run a business. Whether selling merchandise, booking appointments, or collecting reservations for a restaurant, Squarespace has a suite of tools that will help you run an e-commerce site that looks great on desktop or mobile.
Go to squarespace.com for a free trial.
There are a few ways to support us on this show, if you're so inclined. One is to check out our merch store, where you can pick up items printed with stuff that we tend to say on this show. And because we only ever say profound witty things, that place is a goldmine. Another way to support us is on Patreon. Even signing up for a couple of dollars a month really helps. Links to Patreon and the merch store in the description. Now, today, I want to give an extra special Patreon shout out to Gautam Shine, who's supporting us at the Big Bang level. Gautam, if the paper that we just discussed is correct, then humanity is early, and this universe has countless trillions of years of life and civilization ahead of us. While it's daunting to think about producing PBS Spacetime for that long, your help makes it more possible that we'll eventually be syndicated across several intergalactic empires. On behalf of both our present and our far future uploaded or brain in vat teams, we thank you. Today's comment responses are for the episode on the 2022 Nobel Prize, which went to 3 scientists for their work on quantum entanglement. Let's get into it. Moltava, Yavorcha, and Zomg This Is Awesome Lol point out that Einstein was referring to wave function collapse when he said spooky action at a distance, not quantum entanglement as is commonly claimed. Well, yes and no. Now, Einstein was referring to general wave function collapse, in which the wave function appears to change everywhere at the instant a measurement is made, in apparent violation of relativity and the speed of light limit on causal influence. Einstein then got together with Boris Podolsky and Nathan Rosen and basically discovered quantum entanglement in an effort to disprove wave function collapse through a reductio ad absurdum. He showed that the instant collapse of entangled wave functions led to crazy FTL-like effects, and so thought that it couldn't be real. Of course, we now know that these effects are very real features of entanglement, so spooky action at a distance does refer to wave function collapse, including to the wave function collapse of entangled particles. Benjamin Shropshire asks if anyone has ruled out hidden influences travelling from the measurement back in time to the creation of the entangled state. Well, not only has no one ruled that out, it's been shown that this actually works. It's called transactional quantum mechanics. John Wheeler and Richard Feynman were the first to figure this out. They imagined waves travelling from both cause to effect and from effect to cause. If there are multiple possible effects, then the cause gets to sort of choose between them by picking from the time-travelling signals. However, it turns out that the mathematical description implied by this interpretation is equivalent to standard quantum field theory, with the time-reverse signals corresponding to negative frequency waves. Sabina Hossenfelder has a recent video going into the details. It's the one on retrocausality. Jose Martinez asks if there's a problem using random number generators to decide measurement direction, considering that true randomness is impossible. Well, there is potentially a problem, yes. In a superdeterministic universe, the not actually random RNG could be correlated with the event that produces the photons, leading to the violation of the Bell inequality, even if the photon never existed in a superposition of states. But that really appears to require a pretty complicated conspiracy of influences connecting every measurement device with every possible measurement subject, and I've never heard a good description of how the details work. Radar tells us that they plan to dress as a quantum entangled particle for Halloween, and so doing cause lots of spooky action at a distance. This really got me thinking about the other physics-themed Halloween costumes that I could do this year. I considered the ghost particles from our recent standard model Lagrangian episode, a Schrodinger's half-dead cat, phantom energy, Maxwell's demon, or Laplace's demon, and then I figured it out. For my costume, I entered a quantum superposition of both going and not going to all of the parties. This branch of my wave function only remembers not going to any of them, but I assume the other guy had a really great time.